In our next section here, we're going to take a look at some examples on the ASA of using the modular policy framework for inspection, some of the possible problem areas when we run into protocols that do not have application inspection engines, and then how we can modify with the layer 3, layer 4 class maps and the layer 7 class maps in order to do things like HTTP inspection based on domain names or URLs and different other application policies. Now, as we can see from the topology here, right now we have ASA 2 configured as we were previously, where we have the inside network that is attached down to router 5 and 6. The DMZ network is connecting to the ACS server, and then the outside network is connecting to the rest of the hosts. Now, what we should see from the default behavior is based on the fact that the inside interface has a security level of 100, the DMZ is 50, and the outside is 0, that the inspection engine is going to allow flows to go from the inside to the DMZ or inside to outside, then from the DMZ to outside, but not from the DMZ to inside or not from outside to DMZ or outside to inside. So we're going from the higher security level to the lower security level and then returning. If we want to do the reverse way, we're going to have to make a manual exception to the inspection engine with an access list. So first, let's take a look at the command line, and we'll start on the inside network. And we want to know, just can router 5 send traffic out to the rest of the outside network? Now, as I mentioned before, when we look at the default inspection policy on the ASA, if we say show run all, or first let's say show run policy map, it says we have a default policy, which is the global policy. Global policy is matching the inspection default traffic, and some of these application level inspections are occurring by default, like FTP, the sendmail, SQL traffic. Then the DNS traffic we can see is using a preset DNS map. This is where we're calling the layer 7 policy, where the layer 7 policy is then calling a layer 7 class map and doing some sort of specific application inspection on the DNS. So we'll come back to this portion in a little bit once we go through the basic inspections, and we'll see exactly what's happening with the default behavior of the DNS. Now, if we look at the show service policy, we can see what is configured for the global policy and what are the particular packet matches that are occurring here. Now, in addition to the class map inspection default, there is actually a default class here that is matching all of the other TCP and all of the other ICMP flows. So TCP normal applications, UDP normal applications will be allowed from higher to lower. What would not be allowed is an ICMP flow. So if we were to ping, let's say the loopback address of router 2 is 200.0.0.2, we can see that this is not allowed by default. However, if we were to use telnet instead of ICMP, if we're to telnet to 200.0.0.2, since this is a TCP flow, this type of traffic is allowed. Now on the ASA, if we were to turn logging on, if we were to say logging console at level 7 and logging is on, we should see that when the return traffic for the telnet occurs, that this is being inspected and allowed. It says we are building a TCP session that is coming from the inside 10.0.125.5. The source port is 17.8.61, so that's our random port. And it's going to the outside at 200.0.0.2 at port 23. Now we can also verify this if we look at the show connections. It's going to show our active connections. We said show connections all or show connections detail. This is also going to show what is locally originating on the ASA or what is locally terminating there, which in this case would be the EDGRP traffic, the OSPF routing traffic, the RIP routing traffic, in addition to the telnet session that's going through. Now, if we were to do an ICMP ping, so ping 200.0.0.2, we look at the ASA's logs, it says this flow is being denied as it comes in on the outside interface, trying to go to this host on the inside. Because the outside interface, again, is a lower security level, so the traffic is denied as it's going from low to high. Now, also notice that it's not doing an inspection for this. If we were to look at the show connections, or the show connections all, or show connections detail, we're not going to see any information about the ICMP flow. This is because it's not going through the modular policy framework by default. Now, if we wanted to include this, the only thing we would need to do is specify a class that is going to match the ICMP traffic and then inspect that. And in the case of the ASA, we actually do have an inspection engine for ICMP because it knows when a single ICMP echo goes out that the ICMP echo reply should come back in. So if we were to go to, let's say, show run again, policy map, if we were to go to our global policy and we said policy map global policy, we could say for the default inspection class, I want to inspect ICMP. Now, if for some reason the individual application that we're trying to use does not have a match here when we look at inspect, it means that we would have to do a manual exception with an access list. So anything that cannot be explicitly inspected that's not already a standard TCP or UDP application, we're going to have to make manual exceptions for that. So now once the inspection is occurring, from the inside, we should be able to ping to the outside. Then if we were to go to the DMZ link, which is where the ACS server is located, we should see that we're able to ping from the DMZ to outside because the global policy, again, is going to apply to all interfaces inbound. So let's take a look at the ACS server here. If we go to its Windows command line, I should be able to ping 200.0.0.2. So I'm pinging from the DMZ to outside, but I would not be able to ping from the DMZ to the inside because I'm going from a lower security level to a higher value. And if we looked at the ASA, we would see that those packets are dropped as they're coming from the DMZ in. So again, this change in the inspection policy, this is now affecting all of the traffic flows. If we show run policy map, the global policy says now include ICMP. This is applied to all interfaces in all directions. Now, let's say I didn't want to apply this to everything. I want to do a more specific inspection. Maybe I want to allow ICMP pings from some hosts, but not others. Let's say that I want to allow it from router 6's address here, which is 10.0.56.6. And I want to allow this to go from the inside to the outside, or from the inside to the DMZ, but I don't want anyone else's ICMP traffic to be inspected. So this would then mean, instead of using the global policy or using the default inspection class, I'm going to need a new class map that classifies that individual traffic flow, and I'm going to need a new policy map that is applying specifically to the inside interface. So the first step would be to classify the traffic. I want to match specifically the pings that are coming from router 6. So we're going to do this with an access list. I'll say access list ping from R6 is going to permit ICMP that came from 10.0.56.6, and I don't really care where it's going. Okay, as long as it's coming from that particular host. Okay, now technically this is going to be more than ping. It's going to be all ICMP traffic. If I wanted to be more specific, I could say match the type code as well and match just the echo, but don't match things like the ICMP mask reply or the ICMP mask request. Okay, so I have my access list that's classifying the ICMP. Next thing is I would need the class map. Class map, I'll say that this is the ping from R6 class. And inside the class map, we're going to match the individual traffic flow. So again, this is a normal layer 3, layer 4 class, which means that I could match the traffic based on an access list, based on the layer 3 QoS markings like the DSCP or IP precedence values. If it was voice traffic, I could match it on the RTP port numbers. That would be like for video or for voice. Or I could match it on the TCP or UDP port number. For VPN traffic, I could base it on the individual flow or based on the tunnel group. So these we'll look at in more detail when we actually get to the LAN-to-LAN and the remote access VPNs. But in this case, I want to match it based on the access list that I configured. So I'll say show run access list. I want to match based on the access list ping from R6. So now I know what is the particular traffic flow that I want. Next thing is I need to tell it inside a policy exactly what do I want to do. So this is going to be a new policy map that is my inside in. Or I could, more accurately, I could name this just inside because technically the flows are going to be bidirectional. So in the policy map, I'm now going to call the class. The class is called the ping from R6 class. And what do I want to do with the particular traffic? So I could inspect it. I could do QoS onto it, like police it or prioritize it or shape it. I could change the advanced options, set the timeout for them, set the maximum number of connections, the maximum per client. This would be our TCP normalization engine. In the case of ICMP, generally you wouldn't do this because it's not really a stateful, connection-oriented protocol like TCP is. So what I want to do here is just inspect it. I'm going to inspect it and use the ICMP inspection engine. So now the ASA is going to know when one echo goes out, I should be receiving one echo reply back in. If we now look at the show run policy map, we see the new policy I configured inside in is going to match that class from router 6, and it's going to inspect the ICMP. So now I need to apply the policy map to the interface. We'll say service policy. Service policy, it's called inside in, and it's applied to the interface named inside. So here it's looking for the name if, not the actual physical link name. Now notice here that it does not ask me for a direction. Again, the direction of the traffic flow is implicitly based on how I did the access list classification. So based on the fact that the access list is matching router 6's address as the source, it's going to be matching the incoming traffic on the interface. If I matched it as the destination, then it would be matching the outgoing traffic. But keep in mind, once we are calling the inspection engine, this is still technically separate than the security level associations. So just because the policy is inspecting it doesn't mean that the traffic can go from low to high. If I want to inspect traffic from the outside interface in, so let's say that on this segment here, there's a web server that I want to do an inspection for, it would mean that not only would I apply the inspect to either the outside interface or to the inside interface, but I would still need an ACL that says it's okay to go from this low interface to the high interface. So technically, the modular policy framework does not do the permit or deny. It's the security levels and the access list that do the permit or deny. Once you get past that phase, then you can go to the inspection engine. Okay, so now let's look at the show service policy. We see for interface inside, right now it says that no packets have been matched. None of them have been dropped. So if we go to router 6, we should now be able to ping 200.0.0.2. If we look at the counters now, we see that the classification is occurring. Now notice here again that it has been 10 packets. It's 5 out and 5 in. Because for every 1 echo I sent out, I got 1 echo reply back. Again, this is showing us that the inspection is bidirectional. But if I were now to go to anyone else on the inside, let's say on router 6, that I source this traffic from my other interface, that is here 10.0.6.6. Let's see, what does the ASA say? Let's say show connections. And actually what I didn't do, let's say show run policy map. I did not remove the old inspection, so I need to take this one off. Let's say policy map global policy, class inspection default, no inspect ICMP. If we look at the show connections, we can see right now there's no transit connections. It says the ones that are the 5 in use, those would be local connections. If I wanted to see those, I would say show connections all. So now on router 6, I should see that when traffic is being sourced from 10.0.6.6, this is not being inspected. However, if I were to source it from the normal interface, which is the one that I'm matching, 10.0.56.6, this one is matching the inspection engine. So this is simply a basic way that we can be more specific of our classification to figure out what type of traffic do we want to allow, or what type of traffic do we not want to allow. So again, if we show run class map says match the access list. The access list says that it's going to be ICMPs from router 6. If we show run policy map, it says if it is these pings from router 6, then I'm going to inspect it with the ICMP engine. Then this policy is being applied to the inside interface. So if we actually look at the debug now, if we turn logging on and log to the console at level 7, logging console 7, if I do these pings from the correct interface and then the incorrect interface, we would see the outbound connection from the 56.6, this is being allowed. When the return packet comes in, this is what the teardown means. So the echo went out, the echo reply came back in, then the connection is being deleted. What this is preventing against is someone on the outside doing a reverse denial of service attack by trying to flood ICMP replies without the requests. Now, this would also prevent against what's known as either a Fraggle or a Smurf attack. Now, a Fraggle and a Smurf attack, they are reverse spoofing attacks that are designed with either the ICMP echo or the UDP echo protocol to try to flood a particular segment on the network as just a basic layer 3 denial of service. Now, the way that this works is that, let's say that the attacker is on router 4's LAN segment, and router 4 is trying to attack router 6. What it's going to do is source traffic from the address of 6. So it's doing a spoofing of router 6's source. It's then going to send an ICMP echo. Let's say it sends it to this segment here. It sends the echo, but the destination it uses is the directed broadcast of that link. Now, if the host sends it to the directed broadcast, what's going to happen? Assuming that directed broadcast transmission is on, it means that all hosts on that VLAN are going to receive the echo, and they're all going to try to reply. Now, when the reply occurs, they think the traffic came from 10.056.6. So when hosts on VLAN 122 reply, they're actually replying this way. So it's kind of a reverse spoofing attack where the true attacker, which is router 2 or whoever's on the LAN, they're essentially unsuspectingly becoming the source of the denial of service attack. Now, when we get more into network attacks and prevention, we'll see that there's some basic ways that we can prevent this. But the ASA implicitly is preventing against this attack by saying, I cannot have an unsolicited echo reply without the echo request. Now, this is one of the fundamental differences between using an access list for an exception versus using the inspection engine. Because the inspection engine knows that for every one echo, there should be one reply. But if I hit an ACL that simply said, permit all ICMP, then it is not going to protect against this attack. And you can actually try this out on the routers. It's actually real simple to do. If I were to go to router 4, let's say that in my config, I'm going to create a new loopback. Let's say loopback 6 that has the address that is 10.056.6. So it's router 6's address. Now I'm going to ping the address of router 2. So ping 200.0.0.2. Okay, we can see I can send traffic there. But what I'm now going to do is source this from my loopback 6, and I'll give it a high repeat count and no timeout. So I'm essentially just sending packets as fast as the router can. If we look at the ASA, notice what's happening here. It's basically being flooded with these ICMP replies. And the reply is coming from 200.0.0.2. The reply is coming from 2, it's not coming from 4. Now, I may have actually locked myself out of the command line here. Let's say no logging console and see if it'll catch up. This is one of the reasons why you don't want to send the log messages to the console. Okay, normally you would send them like to the buffer or to syslog. Okay, we see 4's attack is still going on. Now, if I were to change this to say access list outside in, permit ICMP any, then access group outside in interface outside. If we were to look at router 6 and look at packet accounting, so let's say, let's create a basic access list on router 6. We'll say access list 100, permit ICMP any echo reply, and access is 100, permit IP any. Then I'm going to apply this in on my LAN interface, so in on fast Ethernet 0/0. What this is going to do is just give me a basic packet counter. So I'll say IP access group 100 in. If we now look at the show access lists, we can see that router 6 is getting tons of these replies. So this would then be the disadvantage of using the ASA with any application that it does not already have an inspection engine for. So if you need to do a manual exception in the access list, you are potentially opening yourself up for some sort of attack, whether it's just denial of service or an application level attack that's related to that individual service. So it's going to be more taxing on the ASA to do the inspection versus just the ACL pass, but you're sacrificing the performance for more security. It's kind of a give and take on the platform there. Okay, now let's look at a case. Does anybody have any questions on this? The the inspection that I did on the ASA here. So again, it's 4 pieces to tie this together. I have the access list matching the ICMPs, the class matching the access list, the policy map matching the class doing the inspection, and then the policy map is applied as a service policy. So this is just our basic layer 3, layer 4 inspection. Now, as for the second part, when I was doing the spoofing attack, the only thing I did on router 4 is I created a loopback. This is the person that I'm trying to attack. Then I sourced packets from this address going to router 2. So when router 2 replies to my pings, the reply is going back to router 6. The reply is not going back to router 4. So we'll look at some more examples of this when we get to more about the network attacks, the way that you can use the network itself to test this out to make sure that the attack is prevented. Okay, so now let's look at another case here where we are trying to send a non-standard application through the inspection engine. And one way that we could test this out is to use the traceroute application. Now, traceroute is implemented differently depending on the individual vendor, whether we're looking at the Unix variation of traceroute or Windows traceroute, where the overall idea is that we're trying to figure out what are the hops in the network between me and a particular destination. Now, the way that this is actually implemented, there's a lot of different ways that you can do it. Okay, but in general, if I'm saying that router 6 is the source of my traces, it's going to send some sort of packet out with a time to live of 1 in order to solicit a reply from router 5 saying that the time has exceeded or that the TTL is expired. Basically, router 5 is going to reply back saying, I had to drop your packet because the time to live is too small. Now router 6 knows that 5 is the first hop in the transit path. Next thing it does is it sends another packet out with a TTL of 2. So now the second hop should expose itself. So on and on and on, it's going to keep incrementing the TTL, sending the packet to wherever the final trace is. Let's say we're tracing to router 4. When the packet actually gets to router 4 is going to reply saying, I'm the last hop in the path. Now, there's a couple different ways to implement this. You could do it with ICMP, you could do it with UDP, or you could even do it with TCP. In the case of Cisco IOS, it uses the Unix variation of traceroute, which means that the outbound traffic is going to be UDP, and the return traffic is going to be either an ICMP message telling us that the time is exceeded, or the final message coming back in saying that the port is unreachable. So essentially, router 4 should reply saying, I don't have that particular service open. So if I send a TCP packet to a web server at port 81, most likely they're going to reply back to me with port unreachable, saying I don't have port 81 open. Now, the potential problem with this is that for this type of application, the outbound traffic flow is different than the inbound return flow. So from router 6 to router 4, the outbound traffic is UDP. So it's UDP that's going to go to some random port value. However, the return traffic is going to be either the ICMP TTL expired or the time exceeded, or the ICMP port unreachable. This is the type of case where a stateful firewall would have a problem understanding this traffic flow, because the outbound traffic is not a mirror image of the inbound return flow. Now, we saw already with our configuration on the ASA that we were allowing ICMP to be inspected as the traffic went out. So on the ASA, I'm going to temporarily remove this access list that is allowing the outside-in traffic. So there's no exception to what's allowed other than the inspection engine. So from router 6, I should be able to ping to router 4. Okay, one of the addresses on router 4 is 172.16.4.4. Okay, let's try something closer. Let's say ping to, let's try router 2. Okay, 2 works, 3 works. Then there may be a routing problem here. And actually the routing problem, that's the previous loopback that I configured, and I need to remove that. Okay, so 6 should be able to ping to router 4. So we know that the outbound ICMP echo flow is getting there, and we know that the inbound echo reply is coming back. If I were to telnet to this address, since TCP is already being inspected, we see there's no problem with the telnet flow. However, if I were to do a trace route to the same address, the flow should be dropped as it tries to come in on the outside interface of the ASA. And we would see this if we went to the ASA and turned logging back on. So logging on, logging console 7. We should see that in on the outside interface, we are denying a couple different types of ICMP flows. It says there is ICMP type 3, code 3. Specifically, that came from 172.16.34.4. Okay, now let's try this again. Let's do another trace from router 6. I should see 2 different types of ICMP flows being denied. It's ICMP type 11, code 0. And then eventually ICMP type 3, code 3. And let's turn logging back off. Now, if we look at exactly where these are coming from, it says the ICMP type 11, code 0. This came in from router 3. And if we would scroll up, we would also see it came in from router 2 also. Then the other type of flow, which is coming from router 4, this is the type 3, code 3. So unless we already knew what those type values are, it's going to be hard to decode exactly what this is. So let's go ahead and look this up real quick. Let's just search for the ICMP type codes. So I want to know what is type 11, code 0, and type 3, code 3. So the official ICMP document, this is via the IANA. They're the one that does the protocol number assignments, remember. It says type 11 is time exceeded, where type 11 subcode 0 was the time to live exceeded in transit. So this is our TTL expired or our time exceeded. And this is the message that should be coming in from the intermediate hops from the source to the destination. Then we have the second code. It was type 3, code 3. Type 3, code 3. Where type 3 is destination unreachable. Subcode 3 is port unreachable. So just as I was mentioning, when we go from the source to the intermediary hops, they are going to be replying with ICMP time exceeded or TTL expired. Then the final hop, which is router 4, should be replying with port unreachable. But now the issue is if we look at the ASA and look at the show connections, the ASA thinks that all of these UDP packets should be having return inbound flows. Now, eventually, these are going to time out. If we look at the show connections detail, we'll see that it says the timeout here is 2 minutes, 0 seconds for this one. Some of the older ones are going to have different timeouts based on the idle time of the actual flow. But the problem is now, the ASA essentially does not understand that the outbound flow is UDP, but the inbound flow should be ICMP. This is the type of case where we are required to use an access list as an exception. There's no other way to solve this type of problem. The reason why is that the ASA does not have an inspection engine for the Unix variation of traceroute. Now, ideally, we would just say inspect traceroute, and it would know for the outbound flows what should the return be. But in this particular version, it doesn't support it. So if we wanted to allow this type of traffic flow to move from the inside network out, we're not having any problems there because we know the UDP traffic, this is being allowed from inside out because inside is security 100, outside security 0. The problem is really that as the traffic comes back in, moving from 0 to 100, the ICMP codes, the type 3 code 3, and the type 11 code 0, these are the two getting dropped. So these are the two exceptions that I would need to make to the outbound interface in. Or excuse me, the outside interface inbound. So on the ASA, I'm going to need an access list. This access list is going to be outside in. It says permit ICMP that is the time exceeded. Okay, again, sometimes this is called time exceeded. Sometimes it's TTL expired. It means the same thing. Type 3, code 3. Then I need to permit type 11. So access list outside in is, actually, I'm sorry, time exceeded. This is the type 11. I need to permit now type 3, code 3, which is part of the unreachables. Now, you'll see, depending on the platform, sometimes you can say the type and the code. In this case, the ASA supports just the type, but not the subcode. Where the router, you could classify both. If I were to say on router 1, access list 100, permit ICMP any, I could say port unreachable, which is that specific subcode as well. But in the case of the ASA, we are saying just type 3, not the subcode. So if I'm going to allow this in the ASA, basically I need to do all of these, which is not necessarily bad as long as someone doesn't figure this out and then do some sort of reverse denial of service attack based on maybe fragmentation needed or source route failed. So these two lines, we're saying permit the ICMP time exceededs and the ICMP unreachables. Now if we apply this access group outside in interface outside, if we look at now the result, now 6 should be able to trace route out. Notice also here that the ASA does not list itself as one of the hops. So from router 6's perspective, it thinks that the traffic is going from itself to 5, then directly to 2. The ASA does not expose its own address in the trace route. So it's a security feature because I don't want people to know what's the address of the actual firewall, because then they could send packet attacks directly to the ASA's interfaces. But again, the key with this is that when we look at the show run policy map, we know what are the default inspections and the exceptions to those that we configured, which in this case was the inspect ICMP. But the ASA is still going to have any problems with a non-standard application that it does not already have an inspection engine for. So remember what we talked about with FTP. The firewall knows that when the traffic goes out as 21, it's actually going to come back in as TCP 20, because that's how active FTP works. If it was passive FTP, it's going to start on 21 for the control channel, and then a secondary channel with a high port is going to go out as well. But unless it can predict what is the resulting inbound flow based on my originating outbound flow, that's where we're going to have problems with this. Now, we'll see this is the same case when we get to the iOS firewall with either CBAC or zone-based policy firewall. Traceroute is not going to be allowed there by default because it cannot predict that based on the outbound UDP packets that we should be receiving the ICMP time exceeded or the port unreachable back in. Okay, there's a question. Is there a facility to inspect non-standard custom applications like NBAR on the router? You can do that just by specifying whatever the port number you want is. So if, let's say we had our web server running over port 8080 instead of just port 80, what I would need to do is say class map HTTP on port 8080. That says match port value TCP 8080 or equal to 8080. Then under the inspection policy, so I'll say policy map global policy, for class HTTP on port 8080, I'm going to inspect this with the HTTP engine. So now it knows that even though 8080 is not the normal port value, I can do whatever custom inspection that I want. So this would be the equivalent of with the IP port map command on the router. So with the router, you're changing what we're matching when we say match protocol. With the ASA, we can just classify whatever we want and then tell it what specific inspection engine to use. Okay, there's another question. This is only a problem for iOS on Unix UDP generated trace routes. Should Windows generated trace routes using ICMP be okay? Well, let's actually try it because we have a Windows machine there. So let's go to the ACS server. This is running Windows 2000. And let's see what happens when we trace route out. So we're already going from high to low. Now, to make sure that the access list I created is not automatically making an exception to this, I'm going to temporarily remove it. So if we show run access group, I'm going to say no access group outside in and interface outside. Okay, additionally, under the default policy, I'm going to inspect ICMP, which means that now the AAA server should be able to ping outbound. Okay, if we ping 200.0.0.2, that traffic is fine. Next, let's go to the ASA, and we'll say logging console 7 and logging on. Then from the Windows machine, we'll say trace route to And actually, before that, let's try something further away. Let's ping 172.16.4.4. This is router 4. Okay, so we can reach all the way there. So let's try this same host, but now a trace route to 172.16.4.4. So it's still being denied. Now, if we look at the, let's say no logging console, if we look at the show connections, let's say show connections all. I want to see what traffic came from the AAA server. Let's scroll back up and see if we can see it in the output. Actually, let's try this again. Let's cancel that. Try the trace route again. It says it built an outbound UDP connection for 200.002 at 53. Actually, that was a DNS resolution first. Then deny inbound ICMP. So what this means is that the outbound flow is using ICMP. The return flow is also ICMP, but they're different types. So Windows is using a ping to go out, which is an ICMP echo, but the inspection engine of the ASA, if an echo is going out, what is it expecting to come back in? Echo going out, it's expecting echo reply to come back in. So the issue now is that it is using ICMP. Okay, that's not the issue. So it is sending echo out, but when router 2 replies, it's replying with TTL expired. 3 is doing the same thing, TTL expired. Then 4 is replying with echo reply. Now this very last reply, this is okay, that matches. This is why when we look at the Windows machine, the only hop that it saw is the very last one. But these intermediate ones that were denied, this is the time exceeded. So it's the same type of problem, it's just we're using a different protocol stack to do it. So Windows is using ICMP, Unix and iOS it's using UDP. Now, you can actually also use TCP to do this. If I wanted to do a trace route to a web server, I could say use the trace using port 80 on the transit path. So that would make sure that there's no disconnect between an ICMP filtering versus the actual application that I'm trying to trace. But regardless, we're going to end up in the same logic problem with the stateful firewall, that the outbound flow is different than the inbound flow. So it's not going to allow us to return this back in. Okay, there's another question here. Would the established parameter help in the access list? The problem is that ICMP is not connection oriented. So there's no way to match the established flag. The established flag is inside of the TCP header. Now, we will take a look at some variations of this when we get to the iOS firewall. And if we're not using like the zone firewall or the CBAC, some of the older iterations, the stateless firewall with just standard access lists, then the first iteration of the state firewall, which is reflexive lists, and what are some of the logic problems that we run into with the older versions versus the newer version.